Welcome to Ask and Learn.
This problem is very similar to the previous problem, but now we are looking for the spring constants so that the amplitude let's see here, the amplitude is again 0.4 meters. And so we have the same system as we had in the previous problem, but now we're told that the excitation frequency is 5 radians per second. The natural frequency squared is 2k because there's two springs, over 50 because 50 is the mass of the weight that's being oscillated. And then again, the excitation frequency, or the excitation amplitude is 0.2 meters. So here is our amplitude of our excitation, delta naught over 1 minus r squared. And r squared is the natural frequency, the forcing frequency squared, 25, divided by the natural frequency squared. So that's where k comes into here. Now, again, we can have either plus or minus, which would give us two spring constants. Let's see here. So the one case where this is the, this would be the, let's see here, this would be the plus, this would be the negative case. We get 417 newtons per meter, and then we could also use the springs with the value of 1250 newtons per meter. And so what we're doing here is we're basically shifting the natural frequency around. So we have our forcing frequency here. In one case, the natural frequency is going to be above the forcing frequency. And in another case, the natural frequency is going to be below the forcing frequency. So we can, again, if we want, this would have a lower natural frequency. So this is when the case in the natural frequency is below the forcing frequency. And actually, that's the positive value here. And then this is where we have a much higher natural frequency, so that it is above the forcing frequency.